Right now, an object from another star system has entered our neighborhood. For decades, these interstellar objects were nothing more than mathematical ghosts. Astronomers knew they should exist, but they were strictly theoretical, calculations on a page rather than things we could actually see. Space is so vast that these fragments can wander the void for billions of years, crossing the light years between stars without ever encountering a solar system. Because of those distances, we built our understanding of the universe assuming our solar system was an isolated box. That box is now definitively open. The process begins during the birth of a star system. As planets form, giants like Jupiter act as gravitational slingshots, catching leftover debris and hurling it into the interstellar darkness. If this happens in nearly every star system, how many of these visitors have drifted through our territory throughout human history, completely undetected? In 2017, we detected an object moving at 26 kilometers per second, mathematically proving its extrasolar origin. Named Oumuamua, its light curve revealed a physical shape never seen before, extremely elongated, roughly 10 times longer than wide. But as it left the sun, it sped up, experiencing an extra push gravity alone couldn't account for. Normally, comets accelerate because the sun's heat boils their internal ice into gas, creating a visible tail. But with Oumuamua, there was no dust tail, no cloud of gas, and no evidence of material leaving the object. Scientists tried to explain this using natural models, suggesting it might be a chunk of solid hydrogen or nitrogen ice that evaporated invisibly. But those icebergs likely wouldn't survive the millions of years required to travel between stars. The physical reality of Oumuamua simply didn't fit our established models of how a natural comet should behave. One researcher, Harvard's Avi Loeb, proposed that this acceleration and the missing gas could be explained if Oumuamua was an artificial solar sail, a thin sheet of technology pushed by the pressure of sunlight. Most of the scientific community rejected this. Radio frequency scans from massive dishes like this one turned up no signals, and critics argued the available data was nowhere near enough to support an alien hypothesis. This left the community in a stalemate, an unproven technology theory on one side and inadequate natural models on the other. 2 years later, a second visitor arrived, 2I Borisov. Unlike Oumuamua, Borisov behaved like a perfectly normal comet. It had a visible tail, a cloud of gas, and it outgassed exactly as expected. When we analyzed its chemistry, we found it was remarkably similar to the comets born right here in our own solar system. Borisov acts as a baseline, showing that other star systems produce ordinary comets, which leaves Oumuamua as a distinct physical outlier rather than a representative sample of what's out there. Now, in May 2026, we have a third visitor, 3I/Atlas. It is massive, roughly 10 times larger than Oumuamua. Because we caught this one while it was still deep in the outer solar system, we have something we never had before, months of warning time to prepare our observations. That timing has allowed for a historic pivot. NASA is redirecting the Europa Clipper spacecraft to study this interloper as it passes. At the same time, the European Space Agency's JUICE mission is repositioning its cameras and sensors to observe Atlas as it crosses the inner solar system. As the comet falls closer to the sun, the heat will begin to boil its volatile ices, releasing a massive reflective cloud of gas and dust. This outgassing, combined with its massive size, means its brightness is projected to climb as it approaches. If these models hold, it could become the first interstellar object bright enough to see without a telescope. We are no longer limited to analyzing cold data from a distance. For the first time, we are chasing the visitor. Objects like these may be more than just rocks. They could be vehicles for panspermia, carrying the organic building blocks of life across the light years between stars. We still have to decide whether these interlopers are simple physics or the remnants of something much more complex. For now, the evidence requires us to remain uncertain. We have 3 visitors, one that was ordinary, one that remains unexplained, and one we're watching in real time. Tell us in the comments below what you think we'll find as our probes close in on 3I ATLS. The data confirms it. Our solar system is not an island. It is a node in a vast, active galactic ecosystem.